Okay, hello everybody and welcome to our second webinar series about GNSS and cellular technologies. My name is Lisa Letzkus. I'm corporate product manager within the wireless team at Rutronik. And today's topic is about precision matters, unlocking the power of accurate positioning and explore the distinctions between GNSS and RTK. We are hosting together with our supplier Cellular, and therefore I'm happy to introduce Eric Lagorge, Global Head of GNSS and Wi-Fi Bluetooth Solutions at Cellular, who will give you insights why higher precision is important to a wide range of industries and applications, and why standard GNSS isn't precise enough. He will also share a couple of use cases and how they can benefit from precision. Later, he will show you Cellular's product portfolio of DGNSS modules and the latest RTK module. Before handing over to Eric, I'd like to briefly explain you the schedule. So first of all, we will record the whole webinar, of course, and you will receive an email afterwards with a link to the on-demand video as well as to the presentation slides. We will also upload the on-demand video on YouTube and on our Rutronik landing page. The whole webinar will be 1 hour, and afterwards we have the Q&A session. So please feel free to type in your questions on the F&A comment field. So yeah, now I will hand over to Eric. The stage is yours. Enjoy the webinar. Thank you.
Thank you, Luisa. So good morning, everybody. So I will start by a brief introduction of Cellular, and I will focus on how the GNSS module, together with our connectivity, our cellular module and correction services, can improve precision and accuracy to centimeter level. I will start by a short explanation of the GNSS source of error, explain the different solution, correction service, and then show the result performance we can achieve with Telit product and correction services. So I will share my screen and remove the camera. Can you see the screen, Luisa?
Yes.
Okay. So let's go. So first, a brief overview of Cellular and how we changed in the last few years from an edge hardware supplier, essentially known for the cellular part, to a full IoT solution provider. So IoT is all about enabling various devices in the field to communicate with the application in the enterprise system. So the IoT value chain is comprised in 3 key pillars: the edge, the network, and the cloud. So the chart is illustrate the ingredient and how they come together. Of course, I will not enter into the detail as not today's purpose, but as you can see, we are able to combine all these key ingredients, to provide to unparalleled support and services to our customer. Starting from the module side with a software added value, then moving to the connectivity world as being a global MVNO, including activation services for the SIM, and our next plus services. And then on the cloud side, our device management portal, middleware platform, enterprise integration services that we provide in this portfolio of product. All these pillars can be used separately. So now let me move to the GNSS. So at Cellular, we offer a broad GNSS module portfolio for IoT application. So this matrix summarizes the different form factor, platform, satellite constellation, frequency, and main feature. I will focus on these two 868 products, multi-constellation and multi-frequencies outlined in red. They are of the Telit flagship 868 form factor, which is the most scalable in the Telit Centurion GNSS portfolio, ranging from standard precision L1 only to L1 plus L5 NAVIC to improved precision L1, L5, and to high precision receiver with DGNSS, real-time kinematic technology, and dead reckoning. So each one of these two GNSS devices, when it's equipped with correction, can bring accuracy to decimeter if we apply the GNSS correction and centimeter level with RTK. As a note, before I forgot, our standard product L1, L5, SE868K5-D can act as a RTK base station. So you can imagine that application can be asset tracking, micromobility, robotic land mover, food delivery robots, agriculture, geographic information system. There are many vertical and many applications. So more and more outdoor applications relying on accurate and reliable positioning have entered in the mainstream. Accurate and robust positioning are one of the key elements that enable smarter and safer modern IoT. These new commercial solutions require submeter and in some cases centimeter accuracy even in constrained environment. The availability to accurately know the location of a device enable new use case and new revenue opportunity for businesses. Let's have a quick view on some of the area where we see the correction being used. Starting from the autonomous vehicle, shifting to full autonomy equipment, becoming a robotic land mover, robotic food delivery robot, so micromobility, e-scooter, e-bike, application on highway navigation, UAV, autonomous drone, AGV robot for agriculture, industrial construction, auto drive system, remote positioning, precision agriculture, smart construction, map creation, location-based device, infrastructure, and building monitoring. Let's take a simple example. Standard localization will put you on the street, but it is not going to put you exactly where you are. And when you look at the visual representation of the difference between meter level and decimeter level, you can see this will tell you, which line you are, which corner of the street you are. And this cannot be suitable for automotive, industrial, logistic application. All of the next generation products require high precision mapping, tracking, navigation, and autonomy. If you take another example on the scooter and where is drop, parking locations are very precisely located and ensuring their user adhere to dedicate micromobility lane and municipal rules that are rapidly emerging. So now, what are the source of error for GNSS satellite? Why is not so accurate? First, the power of the signal from satellite is weak. GNSS device need to see the sky, so it can receive the direct signal from the satellite, but it cannot be always like this. This is not the real use case. So first, the satellite themselves can have a clock and orbit error that can add in a couple of meters of error. And then there are distortions that occur for the ionosphere and the troposphere. The ionosphere is particularly active currently. We see the north light really good showed in lower latitude, and when most of the conditions happen, you see a strong distortion of GNSS signal. And then at the lowest level, there is the environmental impact, such as multipass signal being reflected or obscuration. And then, of course, there is the quality of the hardware design, the software, the chipset used for the module. So standard GNSS isn't precise enough. Standard GNSS could be 3-8 meters in a real harsh condition. If we consider L1 band. Most of the simple receiver having only GPS, even to multi-constellation, even it's offering a fast signal acquisition, better signal availability, but suffer from multipass interference. So if you consider a L1 module only on the real condition, the CEP will be 1.8 meter average, but the 2D error can be up to 8 meter. Now, if you consider the L5 band, additionally to the L1, is better on position accuracy, better interference immunity, multipass resistance, able to track weak signal. Frequency is at 1.2 gigas, so we take benefit of this. And now, if we combine these two frequency on a module, so L1 plus L5, adding also augmentation service like SBAS, we mitigate the negative impact of ionospheric disturbance on positioning accuracy. We mitigate the detrimental effect of multipass. We discriminate between direct and reflected signal, enhancing the accuracy of positioning result. At the end, the CEP for L1, L5 will be below 1 meter on real condition with an average 2D error of 1.5 meter. I didn't consider L2 band as is not, I would say, for a mass market IoT device that require a low-cost solution on hardware. So, sorry, but as you can see, being at, I would say, 1 meter accuracy and with an average 2D of 1.5 meter is not enough accuracy with some scenario to always provide a device with precise location, especially when the device needs to reach below 1 meter or few centimeter accuracy. So GNSS require additional correction. So GNSS correction such as DGNSS, RTK are adopted in many new use cases for more efficient and more accurate position. So what are the solutions for better accuracy? So DGNSS stands for Differential Global Navigation Satellite System, which is a technique used to improve the accuracy of GNSS positioning. It typically involves a base station located as a non-position or cloud-based modeling services that continuously track GNSS signal and provide its correction to the rover. So the rover is the module using a cellular or non-cellular technology. The rover unit also receives signal from the same satellite, but calculates its position relative to the base station. So the RTCM standard define a format of transmitting correction data from a reference station to a rover receiver. This correction data typically include information such as satellite ephemeris, satellite clock correction, atmospheric correction, and other parameters necessary for the rover receiver to calculate its precise position. So these corrections are typically transmitted over a wide area, covering regional for GNSS or even a national scale. So we can distinguish in a way two DGNSS solutions. The minimum GNSS correction, it will limited improve accuracy of submeter to half a meter. It can be delivered using various formats, including MSM1, so the minimum standardized GNSS observation message. MSM1 contains essential information such as pseudo-range measurement from multiple satellites. It is used in differential positioning technique to correct for error caused by atmospheric effect and clock inaccuracy. The other DGNSS correction is the RTK, stand for real-time kinematic. It's the same concept, but adding carrier phase correction. It's using MSM4 to MSM7 message, adding more correction that significantly improve the accuracy of positioning, often to centimeter level. The RTK is severely limited by the short coverage range in terms of 10 to 40 kilometers in the case of core station, which is caused by the degradation of the distance-dependent bases such as the orbit error or ionospheric and tropospheric signal refraction. So RTK technology requires a good view of the sky, proper RF level, constant transmission of RTK to the rover to ensure centimeter level accuracy. So let's summarize this. DGNSS code, use code phase correction, while RTK use code phase and carrier phase correction. So two different hardware. The carrier phase measurement are typically 2 orders of magnitude more precise than the code phase. So the correction allow our Telit Centurion product SC868K5 RTK to achieve centimeter level accuracy with clear signal, while DGNSS correction capability are limited to sub-meter accuracy, which is our SC868 SYD. As I mentioned before, however, in absence of clear signal, RTK suffer more than DGNSS. A poor signal reception for an RTK module means that the quality of the position fix revert from fixed RTK to float with subsequent loss of accuracy. So to make it simple, when you lose the fix on RTK, you are becoming a standard L1 plus L5 module after a few seconds. So what is our value proposition? As part of the, I will say, Telit form factor, this module based on the Aeroa or on the Sony are pin-to-pin compatible. So you have only one footprint to have these two modules on the same design. So the SYD is a dual band L1 plus L5 based on the Sony, supporting DGNSS. We have the SC868K5D, which is a dual band L1 plus L5 module based on Aeroa AG3335 platform, acting as a RTK base station. And we have the 868K5 RTK, which is a dual band L1 plus L5 based also on Aeroa AG3335 platform, supporting RTK. So the SC868 SYD, which is a sub-meter level positioning, support the RTCM 3.3 and accept MSM1 message. The 868K5 RTK, which go to centimeter level positioning, support RTCM M3.3, MSM4 to 7 input message. And then we also provide the Telit Centurion cellular module that will help to demonstrate the benefit of the correction for a centimeter level. So on the Telit Centurion module, we embed, I would say, NTRIP utility for fast evaluation of a GNSS correction. So in one design, we can have two performance levels, sub-meter or centimeter. We can pre-validate the solution, and we provide also cellular connectivity, hosting an NTRIP client utility to connect to correction server. And this is extremely convenient for all the demo. So let me go now briefly on the product. So the SC868 SYD is in Telit compact form factor. It's flash-based. It has flexible software that can be configured and tuned. Configuration can be saved. It supports multiple power consumption profile that can be defined by the customer. It's also support server generating locally, generating prediction for fast time to fix, jamming rejection, jamming detection, anti-spoofing capability. It embeds LNA for optimal performances. You can power at 1.8 or power at 1.8 and 0.8. And in this case, the consumption is probably one of the best of the market. We are at 50 milliwatt with a full constellation L1, L5 in tracking and 36 milliwatt full constellation in L1, L5 in navigation. We also have, I would say, use profile, low power mode available. The SYD also is able to output the RTCM message. So if you have the interest to develop your own application and process the raw data, it's available with the Sony module. So let's move to the RTK. So the 868K5 RTK is as well a dual band multi-constellation GNSS module on L1 and L5. It shares the same compact form factor of the SYD. It also embeds LNA for optimal performance. We also add a pre-SAW filter to reduce interference and best coexistence with cellular. It's an optimal trade-off performance with RTK and power consumption. We are around 70 milliwatt in tracking. We have a second power supply at 1.8 that can be applied for maintaining the clock and retain the RTC of the module. So on this slide, for the next part of the presentation showing a flowchart measurement use case, we will use a third-party correction from Swift Navigation called Skylark. It's a cloud-based modeling. So it allows us to test hardware performance in several locations using several scenarios for both DGNSS and RTK. So to make it short, we will use the Skylark DX for DGNSS service. It's an IP-based delivery solution. So it will typically come over a cellular modem. That means that receiver capable of receiving MSM1 RTCM message that are tuned just for GNSS. There is no content here. So the interface to our server is Ntrip that can run on the host processor, and in our case, will run into our LTE cellular. This service has truly continental coverage and uniform performance through the coverage area. It doesn't matter where you happen to be near of the station or not, because it's a model solution. The performance is completely linear with the coverage area. So typically it's ideally suited for small battery power device, such as asset tracker, micromobility, and wearable. So the SE868 SYD based on Sony is targeting this kind of application. Then we will use the Skylark NX RTK service for RTK, which is a 2 centimeter regional service. Convergence speed must be fast because we've ground infrastructure. So while our newest product in the portfolio, 868K5 RTK, Aeroa base, can achieve a centimeter level with high precision. It's supporting RTCM 3.2 MSM5 data format. The workflow of the correction and how the correction works with our product will be explained on the next slide. So this is how we did the setup and the test. So the GNSS module receive a signal from satellite and achieve standard precision. It's L1, L5 that provide good precision. To exploit the correction, both RTK or DGNSS, GNSS module need to provide its position to the Skylark server and send receive appropriate correction. So the flow, we need to send the GGA message, which is around 68 byte, to the cellular module. Cellular is pushing to the Skylark cloud that is sending, I will say, correction. So the correction is, in the case of DGNSS, 300 byte, and in the case of RTK, which is MSM5, it's around 600 byte. Okay. So we are showing a direction connection using the DGNSS module integrated with the Ntrip client. So N-trip, maybe I forget to explain, it's the network transport of RTCM over IP that suits perfectly in this case. But I would say if you have your own base station, you can use whatever protocol, MQTT or over. So the Skylark engine provides then the correction back to the GNSS module through the cellular. Finally, the correction are processed by module engine and accurate position fix, submeter or centimeter level, that can be consumed on the end device or sent back to the customer management portal. So this is typically, I would say, the demo. So we have a demo app installed into the LTE. In this case, is the Cat1 worldwide. And let's say that it's compatible to any other Telit cellular for evaluating this service directly with including cellular side, GNSS, and connectivity. So this is a few commands to execute to make it happen. Now let's go to some some example. It's I would say we will start by the DGNSS. So it's a good example of the performance of the SC868 SYD. It's for e-scooter application. This particular test case, the e-scooter has to be parked into e-mobility parking. We geofence the upper size point at the center of 1 square meter. We tested 2 modules. One support the correction and one without the correction. So this test has been performed in parallel, and it demonstrates that only with the GNSS, with the GNSS correction, is entering and remain within 1 meter accuracy square. It's important to consider that the test has been done at cold start test. So it means that the module didn't navigate before, so it didn't have any kind of information. For the accuracy, I would say that of the first fix can be like this. It's quite normal for a GNSS solution standard. It's not the best at the beginning. In the long term, the standard solution will converge to a more accurate position in a reasonable time. But you can see that after 35 DGNSS fix, so 35 seconds, only the SYD with correction is able to be on the 1 square meter. So just to another slide to illustrate this, once the correction are applied and the module achieve with a fix of 35 seconds, the module start to enter on the square and remain here all the following time. It's also important to clarify that it's not immediate. It's 35 seconds in cold start condition, but if you are already in navigation before, it will be very faster. You can see that the position average toward 1 meter, while DGNSS achieve half a meter and maintain the accuracy for all. So I put this slide because maybe we can have a valid question. Why do we need a DGNSS service when we can use, I would say, SBAS as a differential GNSS data as zero cost? So as you can see, if you make the test in 24 hours in a real environment, we are showing the percentile as vertical axis and then the meter of accuracy across the bottom. You can see that you have an improvement of 2.5 times better with DGNSS compared to a standard L1 plus L5 plus SBAS. So something also to demonstrate that doing a test in a real test on the city, DGNSS services is I would say you are not obliged to set, I would say, correction each second. We did some test comparison, and 1 second, 10 seconds, even 30 seconds is it's something extremely reliable, and we stay on the line when we are in the city. So in a way, it's important because as you need correction, and in the case you are not using, I will say, Wi-Fi or I will say a proprietary sub-giga correction, and you use cellular, the fact that you can use the correction each 30 seconds will impact your save your battery on the cellular, and also save I will say your data plan in terms of connection. So let me move on this, which is more or less the same. So as I mentioned, if you have a CAT-M modem and you don't want to send a lot of data, it's okay to send the correction 10 seconds, 30 seconds, and still achieve accuracy. Yeah, and if you see 95% of the accuracy at 1 second or 30 seconds, it's still good within 1 meter for an urban within a town. I would say with a mixed environment, it's quite pretty good. It can be highlighted also that even at lower rate, the performance are consistent. So now let's continue to have a look on the real city scenario. Okay, so the blue line is the reference, and the purple line is one competitor that is struggling with what we call a static wandering. This is a very common phenomenon at traffic light, where the position is calculated multiple times and the module tend to shift a little drift. So while the green light is the SYD without correction, and the yellow one is the SYD with our DGNSS correction. So you can see that we are close to the reference, and there is we save more than half a meter. Let's move now to the RTK. So RTK correction are done each second. On the left side, we see a 24-hour static test, and in this case, you can see that the accuracy, I would say, is around 90%, but giving, I will say, 1 centimeter accuracy. While even if you go on the right, a 15-minute test, the results are aligned with our best class competitor. Let's say 95% will be around 2 centimeters. This is a static test. So let's move now to the next slide. So the next slide, it's a demo done by our application engineering team testing the accuracy of the RTK, just replicating the Telit logo on the 30 centimeter and moving the antenna. So you can see that it's extremely reliable, and below 2 centimeter, I would say 98% of the time. So now let's show some 868K5 RTK performances. So the first test has been done in open sky, and you can see that there is a perfect overlapping with reference. So this is the perfect scenario. Now let's move and let's go on the city and do a test with a competitor. Okay, so you can see that it's perfect on the street, perfect on the roundabout. Let's put now the same module on the same condition, which is our 868 RTK, and let's make a fair comparison that competition or our module applying the same correction in the same environment with the same antenna, you can see that it's perfectly overlap. Now, something in, I would say, RTK in urban test. So RTK is completely overlap on the street, and when you enter on the, I will say, the tree line, you can see that there is not a perfect overlap. So you have 95% accuracy at 2 centimeters, and then after that is moving up to 10 centimeters. I cannot zoom on the slide, but we see the first impact of the, I would say, on RTK when you start to have some tree like this or some building, you are losing some centimeter accuracy. After that, if you do this test in a woodland scenario where the signal is heavily affected by tall tree, the receiver dropped out of RTK for both. Okay, so good condition, it's perfect match 2 centimeters. Then when you start to have some tree, less signal, you are moving maybe up to 10 centimeters, and then after that, on the very bad condition with a tall tree, the two receivers are dropping from RTK and are back to standard L1 plus L5. So just to show you the tool we are offering with the cellular and so on. This is a demo how to test a DGNSS, but it's valid also for RTK. Everything is integrated into a TELIT tool. So more or less, the idea is to support and see, I will say, all the satellite use, and then after that, launch some session using the Sony with DGNSS correction or the RTK with the MSM5 connection. So you can see that after, I will say, convergence of a few seconds, everything will be on the 1 meter accuracy for a DGNSS. And this test has been done in live condition. Okay. Next slide. So it's almost done. So I would say in terms of conclusion, everything what I present in terms of module, AVK, demo are available. I just want to add that we use one correction provider because it allows us to do the test in Italy, in Taiwan, in US, everywhere to see the consistency of the module. But our module are completely agnostic to any correction provider. Okay, as they comply to RTCM 3.3 input-output message. All the correction can be done locally with a base station or a different provider. We test in different area, and we see the same range of result. So it's consistent. As a side note, RTK technology requires a good view of the sky, good design, good antenna, and proper RF level. And you need constant transmission of RTK correction, so each second. While DGNSS is maybe less accurate, but it's less sensitive, I would say, in harsh environment, and does not require a constant correction. That's all from my side.
Okay, so thank you very much, Eric. I think let's directly jump into the Q&A session. We have some questions. So start with the first one. Can TELIT SE868K5 RTK with different RTK correction provider?
So the answer is yes, because we test several providers. Yes. It's the module is completely agnostic. Okay.
Then the next one is the competitor mu-blox.
Could be as a reference. Yeah.
Then the other one is what happens outside of the coverage.
So this is, I would say, when you use the DGNSS, is a national coverage. Okay, so you don't have any surprise. After that, when you use, I would say, correction service for RTK, and you want to reach 2 centimeters, you need to have the base station as close as possible. So I would say in the range maximum of, depend on the receiver, but up to 40 kilometers. So if you don't have, I would say, if you are relying on the service provider, the first question will be, do you have any base station installed on this area? This is the first question to raise to any provider. If you build your own base station, your own network, I would say it's your responsibility after that.
Mm-hmm. Then another question, is Skylark available for Telit customers? If yes, at what price?
So in fact, to allow the customer to make, as we are not able to provide base station, we just have the module acting as a base station. In our AVK, we provide also the possibility to use a Skylark for test, and it's a voucher with a data code, and it's I would say it's one, if I'm not wrong, it's 1 month free subscription, and then after that, if I would say you as a customer, you want to extend the test, you just have to ask Swift to extend. Okay.
Mm-hmm. Then the last question, what are SE868SYD and SE868K5 DGNS and RTK data plan?
So I will give you the maximum. Okay. So when you send a data to the server, a GGA sentence is 68 byte. Then if you download the GNSS correction is around 300. And when it's RTK, it's 600. So I would say RTK, if you do each second correction full day during 24 hours, during 1 month, the data plan will be maximum 1.7 giga. But there is no application that you are working each second 24 hours during 1 month. Okay. DGNSS, so we are at the level of 1 giga more or less. If you consider DGNSS, so I would say the data, it's only 300 bytes in download, and you can apply each 10, 30 seconds, even 1 minute. So you are in the range of 10 mega, 10, 20 mega, 30, depend on your application. But it's an easy calculation to do. We can help for that.
All right. Then there's another question, how easy it is to create our own base station with the SE868K5?
So you know, we provide the module. After that, you just have to add, I will say, a connection to the rover. So the connection, if you are close, can be on Wi-Fi, can be on LoRa, can be on cellular if you are far. There is no complexity for that, I would say. Us, we just provide, I will say, the module, which has a specific firmware, allowing after that the rover to make the correction.
Mm-hmm. All right. So thank you, Eric, for answering the questions. These are all questions. So just before finishing, thanks to all of you. Thanks, Eric, for the presentation, for the insights. Thanks for all participants. And I'd like to just quickly show you our different channels where you can get more information. Just visit our Rutronik webpage or our Rutronik 24 web shop, as well as our tech.com homepage, where we write articles about the latest products of our suppliers. And of course, we are also available on social media. Later, then before really finish, I want to give a short, you can also, of course, get into direct contact with me as corporate product manager, or fill out the contact form, or get into direct contact with your Rutronik sales agent. And now I want to give a short overview of our upcoming webinars. So today in the afternoon, we have another webinar about RTK, as all constellation multiband RTK technology, centimeter level positioning from Unicore Communications. And then on Wednesday, we have Nordic webinar and Kyocera AVX about the antennas. On Wednesday, free sessions with Cellular about the IoT terminals and gateways. And on Thursday, the last webinar with Nordic Semiconductor about DECT NR+, the world's first non-cellular 5G standard. So feel free to join to register here with the QR code on the right hand side. And we're looking forward to your participation. And thanks to all of you. Goodbye.
Thank you. Bye-bye.